Good morning, everybody. Did you hear me from the Zoom?
Yeah, I can hear.
Okay. Welcome to the course.
Thank
This
you.
for the institute is a very unusual course in the sense that it's very long in time. There will be 2 months, and that's because the topic is very broad. So to cover it, we need time, basically. And in spite of being long, large, it's going to be intensive. So it will require that you spend most of your life, your time in doing this course. There will be homeworks and there will be labs. So you have to. The labs are the homeworks are for topics from the analytical part, and the labs are the applications on the computer. Mm. So we will be going that way. In, it's going to be in parallel. It will take some time for us from the theory to reach the point where we can do real things, but in the meantime we are going to learn the language, the computer language, and we are going to do some small things so that we are preparing all the material. Also at the beginning, the material that we are going to cover, most of you already know it, linear algebra, topology, some functional spaces. Um, so we'll go more or less through all this material. So do you have any questions?
About the computer, so we need to bring our personal computers, right?
Yeah, it is better. Yeah,
Okay.
yeah. This afternoon we are going to have a session for installing and trying Julia, which is the computer language we are going to use. So we are going to meet from 3 to 5, and so if people have problem installing it and so on, we can help. And we'll provide the first lab, which is just to get used to it. More questions? So Virginia says that she cannot hear. Does the rest hear?
I can
I
hear.
can hear you.
Okay, okay. Alma is not hearing. ¿Está o no?
I can hear, but the volume is low.
The volume is low. Okay. Let me see if I can figure out how to. Not from here. Maybe from the computer. Hello, hello. I think the volume is okay here. Maybe I can move the microphone this way. Now? Now? Did you hear better this way?
For me, yeah.
Alma, and can you hear? Okay, what can we do? Now, Pablo, can you ask the guy to raise it? Because I don't know how to do it. We'll try to raise the volume from the... Yeah, it's not that I'm using my computer microphone, I'm using the system here, so I will call the guy that does this to maintains this to raise the volume. Can you raise the loudspeakers? I think they are doing something now. What about the screen? You see okay the screen?
Hello, good morning.
Hello, morning. Can you raise the volume or is... Because they're complaining that they cannot hear.
Okay. Is your volume to the room or to the Zoom people?
To the Zoom people.
Ah, okay. Can you try?
Hola, hola. Hello, hello. Hola, hola. Hello, hello, hello. Did you hear better now? So
It's
there are
better
people.
now.
You can speak now.
Hello, hello. Now
I
there
can
is
hear
people.
well.
What did he say? There was some...
I suppose that someone spoke on your phone.
Yeah, but I couldn't. Okay, most of the people now says it's okay. Anna, is okay for you? Alma? Virginia? Okay. Thank you.
No problem.
I think it's okay now. So, any questions about the course, the material, the homeworks, the labs, etc.?
I have a question about the lectures.
Yeah?
So how long? So do we have 4 hours of lectures every day, or how is it?
Yeah, from Monday to Thursday.
Okay, so it's 2 lectures of 2 hours each every day.
Sorry?
It's 2 lectures of 2 hours each every day.
More or less, yes. Maybe 4 lectures of 1 hour or something. It depends how
Okay,
people
perfect.
feel. But
All
it's
right, thank you.
okay. More questions? Okay, if not, we can start. Today we are going to start with linear algebra. So most of you know linear algebra very well, but I want to start with the same notation and going through the things we are going to need in the course. So just not to start with the, say, self-adjoint operators or something like that, or Jordan decomposition. I will start from the beginning, and because we are only going to use in several aspects of linear algebra along the course. So usually I teach first topology, but this time I want to start with linear algebra. But there will be some things that I cannot prove or mention at this point, so we have to wait until tomorrow, say, or the day after tomorrow, that we can have topology also. And topology is important for this topic because besides the usual topology that we are used to when we have spaces with norms, in some cases we have weak topologies that do not arise from norms, and we have to understand a bit about that. And also because it's nice. So let me start with the linear algebra, just from the beginning, vector spaces. So a vector space, and here I'm meaning a real vector space, then later on we are going to talk about the complex ones, consists of three things: a set B, which elements we call vectors, and two rules. One that assigns to each part of vectors a third vector, and this assignment we call B plus U, and call it the sum, and a rule that assigns to each vector a number, a real number A, a vector which we will denote by the product. So this is, here I don't have it, but it's A times B. And these assignments have some rules. The first one, that this assignment is symmetric, so if we sum U plus B is the same as U plus U. We have a zero element, so an element that if we sum this element to any other element, it gives the same element. An inverse, a unique inverse, which will denote by minus U, so that U plus minus U is zero. And then for the multiplication, for the product, we have these rules that is the same: first to multiply by I prime and then by A, and to multiply the numbers first and then multiply by the vector. So here we are using properties of the reals. And there is, and the one is just identity. The number one is identity. And then we have these two properties that basically what they say is that the operations are linear, that the sum is linear. So if we have a couple of numbers and we sum them and multiply by B is the same that multiply first the numbers by each one by B and then sum. This is a vectorial sum, and this is a product times, it's a product only, and this is a product and plus a sum. So here we are mixing the two assignments, and then we have this other one, right? That if we multiply the sum of two vectors, this is the same as multiplying first each vector and then summing. Okay, so these are the properties. And then we have examples. The examples that everybody knows are tuples, and so you have some list of numbers, A1, A2, A3, AN, and you sum with some other list. And the sum is just the sum, right? AN plus BN, etc. So this is the usual thing, and this is what we have in the computer in some sense. We have arrays in the computer, although in the computer they are not real numbers, but they are computer numbers. And this is the standard example, but this is a much better example because it's a universal example. In this example, you have a set S and functions from or map from S to the reals, right? And this function, since we are going to have a vector field, we call B. This we will call F, but let's here call B. So we have functions, right? And so we have, say, a function that takes some element of this space and give me a number. And you have another one with some saying I give you another number, right? So now we can define the sum of vectors, right? And the sum of vectors is as follows. B plus B prime has to be a function, so it acts in elements of S, and this has to give me a number, and the number that gives is Bs plus B prime S. Right? This side we have numbers, we know, because we have these two functions, and here we are defining the sum. Okay? That's the usual thing when you think of functions. That's what I do. But here we are just having these abstract things on some set, which can be finite dimensional, infinite dimensional, etc. And we are defining this action. The same some number by B is a function that acting on some element S give me the number alpha B of S. So in this side of the equation we have numbers, and here we have functions applied. It's okay? And you can check that this set of functions from S to the reals, all the functions together, they form a vector space. And there is a theorem that tells you that any vector space can be realized as some set and functions from that set to the reals. So in that sense, it's a universal construction. Every time whatever you have, for instance, the example we have before, what will be? How do we get the example we have before? The tuples. With this construction. Any idea? We'll say we get some finite set of S1, S2, Sn elements. And so now if I need functions from here to the reals, I can take, for instance, the functions B2 of S, this function, since B of B2 of S1 to 0, B2 of S2 to 1, and all the others to 0. B2 of Sn to 0. Right?
So, is this a way to construct like a scalar properties?
No, it's just vectors. There is no scalar products.
Because it feels like a scalar properties. You take, I mean, V2 is a vector, it's not a component, but you could think as V2 as an element of the basis. I mean, you didn't mention basis yet, but it could be an element of basis, and then you could construct sums of like V1 plus V2 and
Okay. Yeah, you can think of that way. It's not quite a scalar product because the space of the components is different from the space of the vectors. But yeah, you can do all this identification. So here I'm building a base, right? A base Bi is the base applied to S is Bi of Sj is equal to 0 if I is different from j, and Bi of Si is equal to 1. And then I can write any vector, any function, B of S as a sum of some elements times Bi applied to S. And this way I can build any one, right? So these vectors are the same as the tuples in a base. And this is what you thought as scalar product of A times the base. But these are numbers and these are vectors. So the sum is a vector like that. And when you apply to S, it gives you a number. Yeah. So this is the universal construction, and we are going to be in the course we are going to be using S to be finite for some part of the course. So finite dimensional vector spaces, and then we are going to use at the same time in another context with S to be infinite, say the real line or the Rn, or things more complicated still. But we are going, everything is covered by these vectors that are the same mathematical structure. Although I'm going to tell you what is the difference according to whether they are finite dimensional or infinite dimensional. And then there are differences. And here we are going to talk about bases. We say a set of vectors are linearly independent if whenever you have this combination equal to 0, then that implies that all AR are 0. So this is linear independence, and then we say that a set of vectors span some subset of B. The span is just a linear combination of these vectors. So the span of this set are all linear combinations of the II. So things like that. Sum of over I to n, the A, I, Bi, for arbitrary I. And that, here I'm saying in the finite dimensional, but the infinite dimensional is the same, because unless this set is infinite dimensional. And then I cannot write like that with a finite number. I have to use take infinite sums. And this set we are going to call the span of U. And we say that a set of linearly independent vectors is a basis when the span of this set is the whole vector space. And in the case that this set is finite dimensional, we say that the dimension of B of this vector space is n. So we have some UI, some set of vectors, each one belonging to n, when the span, and they are linearly independent. When the span is equal to B, then we say that this is a basis. And we say that the dimension of B is n, if they were n vectors, I equal to 1 to n. If we need the infinite vectors, we say that the space is infinite dimension. Okay to here? Now we are going to see 3 ways of building extra vector spaces from one vector space. The first one is the dual, what is called the dual. So I have a vector space B, and I want to build another one that I'm going to call B star. And this is, we're going to use this strategy of getting all functions from this space. I could consider, say, all functions from B to the reals, but I'm going to consider only the linear functions. So I'm considering now all linear functions from B. And this is what I'm going to call the B star space. So I have remember we have a S, and we have the functions F from S to the reals, and the set of all these were vectors. Now we are doing something further. We are restricting the F to be linear. Linear, what it means, that if I have, say, an element of these functions, I'm going to call them omega, say, taking 2 vectors, 2 different vectors, say, and multiply it by a scalar. This is the same as a function omega of B plus alpha omega of U. Only I restrict omega to be linear so that they satisfy this. Okay? Yeah.
So, a vector space, and we tend to think as vector spaces as spaces with a linear structure. But then you said that this function omega, we choose it to be linear, but it is not necessarily a condition for it to be a vector space.
Well, one thing is for the operations inside the vector space, for only linear operations. The other thing is the function itself is linear. For example, you can think of all polynomials as a vector space. The polynomials are not linear on X, but the polynomials itself as a vector space, consider symmetry polynomials, that is a vector space. And those operations are linear.
I suppose this is a nice example. You take the polynomials, right? These are functions from the real line to the real line. And this is a vector space. What is the sum? You just sum the polynomial to get two polynomials and sum every power, right? The coefficients of every power, and you have another polynomial. So this is a vector space, and you can multiply a polynomial by some number, and you multiply every coefficient. So it's a vector space. Now we are restricting to the polynomials which are linear, so are just x, say, right? So, but we are not restricting to be in the real line, but in some other space which is this V. So now we take from, and the linear polynomials are a vector space also, because it's a sub-vector space. Because if you take two linear polynomials and you add them up, it is also a linear polynomial. You multiply by something a linear polynomial, you get a linear polynomial. So it's a subset. So it's a sub-vector space.
But this space, the dual space, it needs to be linear in the sense that a function applied to a sum of two vectors should be the sum of the functions applied to vectors.
Yeah.
But that is not true generally for any function that you define over the vector space. Maybe that doesn't hold.
Yeah, so we restrict to this. So this is a sub-vector space from the big one, and as we are going to see, suppose take the following, the example we just mentioned, take B to be the real line. That's a vector space, right? Because you can add, it's a tuple with one number, one tuple. And then all the functions are every function you can imagine, right? Even the discontinuous function doesn't matter. They have the structure of vector space. Because if you have two functions, you know how to add them, and you know how to multiply them by some scalar, right? So it's a vector space. And now we say, okay, we are going to take only the linear functions. The linear functions on some number by x, right? And we have different numbers. So if we restrict to that, we have a one-dimensional vector space, because again, we change this number and we change the vector. All the vectors are some number by x. So if we choose this number, it's one-dimensional thing. Huh? The basis there is x, say. 1 times x is the basis. Right?
Another simple example is you could think of a function that takes any vector and returns 3. The sum of the function applied to the sum of two vectors is 3. The sum of the function applied to each vector is 6. So we are not considering only the linear.
So then this is the vector, the dual space is the space of all linear functions on the vector space. Huh? And this sometimes is called covectors, because it's a vector space that comes from another vector space. So the elements here, this omega, are called covectors. And so we have these functions, and here we are just repeating what we say about the functions in general. Remember, we define the product of a covector by some real number plus another vector as a function that applies to B, give me omega of B, this is a number, times plus alpha times tau of B. These are numbers in this side, and this is a function applied to B, right? So when we want to define a function, what we need is to know what the value is for every vector that we take. And the value is this one. That's tricky, but it's very simple, but it's a bit tricky. You have to think a bit on how to you build things. Here is everything is defined. So we can ask, what is the dimension of this space? For that, remember, we have to find a basis of linearly independent vectors that span the whole space. A basis, a set of. And so we do them as follow. This is a definition. These are functions on the space V. These are the functions that when taking the vector of a base, say we have a base for B, n elements. So B is n dimensional. And we define these functions. This is not a computation, it's just a definition. These are functions whenever they take the base, if they have the same index, then they give you 1, otherwise they give you 0. Right? They are not, there is no computation here, it's just a definition. And so now we have to see, the claim is that these vectors, these covectors, are linearly independent, and they span the whole space. So every function you can write it down as a linear combination of these vectors. Huh? Clear? That's what I need to do. So first we say, okay, every linear combination, we get the sign of some numbers. This equal to 0, and I want to show that all the alpha I are 0. So this is a function, so I apply to a vector aj, and this is the delta, so this sum is just alpha j. And since this is 0, this implies that this vector is 0. This number is 0. Okay? So I show that they are linearly independent. And then I need to show that any vector, any covector, can be spanned as some linear linear combination of the base. How do you think you can do that? How can you prove this?
Expand the vector B into the basis.
Yeah.
Linear space B, and then you use the fact that theta I is linear also, and that theta I of which one of the basis vectors is the delta.
Right. No, that's a way. So you say rho, you expand this in the basis like that, and on the other side you get. So here I'm going to skip the sums. When there are indices which are repeated, I skip the sum, so I don't have to do all the sum all the time. It's okay? So this is rho I, theta I, there is a sum here of bj, aj, sum here also. And now we use linearity. Since these are real numbers, and these are vectors, I can take this out of here, right? So this is rho I, bj, theta I, ej, theta I, ej, and this is delta, so this is rho I, bi. Okay, so this is the representation of my function in terms of these components of the vector and these components. So any function on this space, any covector can be represented in this basis. Another way of saying this is the following: you take, no, that's okay. What about the people online? Are following okay? Let's see if I can see. There will
Yes,
be
it is clear.
Okay. Okay, I continue then. We are going to make a break at 12 at noon for 15 minutes, and then we continue until 1 o'clock. So here we have exercises for you. Just repeat what we did. Prove that V star is a vector space and that this really is a basis. You have to think about for a while. Prove that if you want to write a vector in terms of the basis, then these components of the vector in that base, you can find them as this way. You act with every element of the cobase of E with a B, and that gives you the component of the vector. So remember that we say, okay, let's B be the vector space of functions from S to R, where S is a finite set with n elements. Here is a base for this set of vectors. Find the corresponding cobase and of the dual space. So think about the dual space of this space and find the cobase. So this is a construction. We have B and we have built the B star, the dual space. This is dimension, in finite dimensions, this space's dimension is n, and this also has dimension n. And if we have a base for this one, we have the corresponding cobase. So if we have an element here, a vector B in this base, we write like this. These are the elements of this vector in this base, the components. Then we could, in principle, say, okay, look at this vector, which is sum. I'm going to put the sum here now because they have the indices in the same position. Oh, I could write this, and this is a covector, because it's a linear combination of covectors. So we have here a map from B to B star. So in general, these spaces are the same thing, are the same. They represent, every vector I can represent by tuples and tuples. But this assignment, this function that I'm building here with the E and the theta, is not natural because this is a basis. If I change the base, the assignment changes. So there is really not a natural assignment between vectors and covectors, right? They are not the same thing. They are not the same elements. If you go to geometry, ones are vectors and the other are forms, so they are different. Geometrically, they mean different things. Vectors you use to think of arrows, and covectors you think of piles of planes. So they are different. The geometry that they give you is different. And in mechanics, say in physics, you have vectors are velocities and covectors are momentum, which are things which are very different. They are only similar in very particular cases, right? In free particles, basically, and then they are not the same thing, right? So one are vectors and the other covectors, and that's the difference. So mathematically, the difference is that if there is some other element, we can do some identifications that are okay. For instance, in mechanics, if you have a metric and free particles, then you say, okay, vectors and covectors are the same because you use the Euclidean metric to see that vectors and covectors can be mapped one to the other. We are going to see that in a moment. But in principle, they are different things. And sometimes it's useful to think of them as different things, not mix them. Because unless there is something natural to mix them, some other structure, they are different. Here I'm following, you see this text, I'm following here is, I have a set of notes in Spanish for courses I've given in the past. So now I translate them with the Copilot artificial intelligence, all the notes to English. So there might be many mistakes or things that we don't understand. So if you find them, these notes are available in some GitHub repository. So if you find them and read them and you find something that doesn't make any sense, probably it's the artificial intelligence, or probably they're wrong. So in any case, just tell me so I can arrange them, correct them. So this was one way of, you get a vector field and now you build these ones, they are functions, linear functions. On B. Now we can do something else. We can take several copies of B. Before going to that, suppose now I have B star, they are the same dimension, and then I can take B star of the star of B star, right? Because this is a vector space of some dimension. I can take all the linear combinations, linear functions on this space. do I get something different this time? A different vector space. If I am in infinite dimensions, I can get different things. But at infinite dimensions, I don't. I just get B again. So there is a natural identification between these two spaces. So I don't get anything new. How does it go? So let's call these elements with the capital letters, X, say. I can have some X, which I'm going to put a B here, which are the same, the following. When acting in an element of here, it gives you some number, and the number that gives you is omega of B. So I'm saying, what is this function in B star? It's a function that takes this element of B star and give me this number. Okay? Is it linear? Yes. X of B of omega plus alpha tau is equal to the number omega omega according to the definition applied to B, and since this is linear, this is the operation, we already know what is this, is omega of B plus alpha tau of B. Numbers, huh? And this here is xb of omega, and this here is alpha xb of B. Huh? So it's linear. Of tau, so tau. Right? So these functions are elements here. So the set of all xb, let me call big B means all the elements of this form, where B is an element of B, is contained in X and B dual. Right? So all these are contained here. And this, now so I can think of X, this X as a map, right? X that sends B to B dual. Let me call this like this. Right, because every time I get a vector B, I put it here, and I get an element of that. Right? So I have this one here. I took a B, an element of this space, and I formed an element of that. That element was this. It has a definition. So this thing here, it lives here. So I can think of that X as functions that takes one element here, which I will put it here, and give you an element here. So it's a map from B to B star. Okay? The claim is this map is injective. What it means? Everybody knows what injective is. Huh? Here, what we have to prove is that if x of v on omega is equal to 0 for all omega, then b is equal to 0. Right? That will tell me that the map is injective. So the map that sends everything to the 0 is the map, the 0. And how do we prove that? Well, remember that this here is just omega of b. If omega of b is equal to 0 for all omega, then this b has to be 0. Why? Because remember, omegas are all functions from the space B to the reals, right? So I have to apply all functions. So if all functions on B give you 0, that it means that B is the 0. Okay? Because so you give me one B, there is a function that sends, in general, function say hat, one particular one, that sends this to the number 1, right? It's a linear function. So, since this is true for all B, that means that this has to be 0. The B has to be 0. That's the only way. So that everything gives you 0. So we have but now what is the dimension of this space, of this V star? The dimension of this was n. The dimension of the dual is n. So the dimension of the dual has to be n. Right? Because this is a dual of that, and we saw that every dual has the same dimension that the parent vector fields. So here we have an injective map, and the dimensions are the same of both spaces. So that means that with this map, I can cover the whole space B double dual. So not only we have this, but we have the identity that xb is equal to B dual of the dual. Yeah. Is it clear, this? Or no? So we have two spaces, the B and the double dual. And we say, okay, we have a map that sends every element from here to this element here. That is a map X. And this space has dimension n, and this also has dimension n. And the map X is injective, so the only element that goes to the 0 is a 0. Right. Then the rank of this map is dimension n. So it takes the whole space. Remember from algebra that the rank plus the kernel of a map is equal to the dimension. Here we say that the dimension of this is 0, so the rank has full dimension. And so xb is a whole space. So we'll make an interval, pause, until 12:15, okay? So we meet in 13 minutes.
Oscar, I have a question.
Yeah? If we don't forget, so if just remind me to press the button here. Okay, let's continue then. So we see that if just taking the duals, it only produces one new vector space, this one. This one is not interesting because it's basically the same. But let's see these things. Oh, here is a thing about the basis that we are going to use in a moment. So let me have it now. Suppose you have a base for B. Then you have the base, the co-base, the base coming from this one on the B star. And then you have a base coming from this one in the B star star, right? This one satisfies this. So our functions on vectors will give you the identity. And this one satisfies this. So our functions on covectors will give you the identity. So a covector you write this way in the basis. And you can see that if you take this sigma and apply aj to sigma, you get the component, right? Because aj of theta is just delta. So this way, if you want the component of that, you have to take this one. Now, if you apply sigma to aj, this give you this one, and it's also give you sigma j. So this is the relation between this base in the co-space and this one here. That give you the same thing, the same number. Because this property here, right? This is this one, apply to this. So this base is actually tied to this one, in the same way of that we say the x of ai is ai. We are sending them by the maps, these maps x from B to. Remember that this was a map from B to B double dual. Okay, so what we can do now is the following. We take k copies of B and L copies of B dual and look at all the functions from this space, which is bigger now, to the reals. So this will be something that's called T, which has one up to k slots for vectors, and then you have L vectors, L slots here for covectors. And you look at all the maps that are linear in every one of the entries. On each entry. So for instance, you can take something that takes two vectors, u, and give you a number. And it's linear. What it means that T of B plus A of W times U is equal to T of B U plus A of T of W U. So these are, and in general you will take any copies, k copies, L copies, and make some B's that can have, it's a linear map from all these things to the reals. These are called tensors. and they appear a lot. For instance, I can take suppose I take, let's play a bit. Suppose I take a tensor that takes two vectors, huh? U and B, and give me a number. If I forget to put one of the, I just put one vector here, and I look at this, what this is.
This is a dual vector, covector.
This is a covector, right? Because takes a vector that I haven't put here and give me a number. So this thing is a covector, sigma, say. So every time you have one of these, you have a map from B to B star, right? Because I put something here and it'll give me a vector, a covector. Right? If this map is invertible, then I have a relation also on the other way, right? Then I identify vectors with covectors because the presence of this thing here. So for instance, every time I have a tensor that takes two vectors, then I have a map from B to B star, B dual, and if that map is invertible, then I have a map on the other direction too. And so I can, every time I have a U, I can think of a covector and vice versa. So I can identify these spaces. This happens, for instance, in mechanics when you have a metric and the space-time, then the vectors and covectors, you can think of the same thing because there is a metric that connects them. If we don't have this thing, then we don't have that connection. This connection can be through a metric, a symmetric tensor, or could be also through an antisymmetric tensor, a symplectic structure, for instance. Not necessarily. The only thing we need is that is invertible, so that we can go from vectors to covectors and vice versa. What will be this one? This one, A takes a vector and a covector and give me a number. If I remove the sigma, what do I have?
You have an element of B star star.
Right. This belongs to B star star. But since this is the same as B, this you can think of a map from B to B. What are the maps from B to B if you look at the inner basis? It's a matrix, square matrix. So all these square matrices, maps from B to B, operators, what we call, they are included in these tensors. They are particular ones. Let's look at the following. I don't know whether I have here. Well, this is just what we have before. This is a case of a metric. So if you have say a T, I'm going to change colors. This I don't like. A T that takes two vectors. you require this to be symmetric, so that T of this is equal to T U of B. Here I see I spot a mistake here. This twiddle here shouldn't be here. I have to remember. Oh no, it's okay. We can require this to be symmetric and say this to be positive. That is, if I put the same vector in both, this is less or equal to 0 only if u is equal to 0. Then I have a map, right? That sends vectors to covectors, and this map is injective. That is, if this is 0, for all well, I have here the calculation. Maybe it's easy. I have to prove that the injectivity is this. Injectivity is easy because it's positive. So if I put the same here, and this is equal to 0, means that B is equal to 0. So I have there a map that sends that is inverted. So I have a map not only from B to B star, but the inverse map sends me the other way around. And so, for instance, if I have as a vector, I can create the covector like that, and if I have a covector, I can get the inverse of this map and create a vector. So then I say that these two things I call the same, and continue working. Yeah.
So this result of using this condition that when you pick a tensor and you apply it for the same vector twice, you get 0. I can think of it as a metric on a Euclidean space.
Yeah.
But we usually do that in relativity too, even though that there are vectors that have length 0 that are not the identity, they are not the
Yeah.
they are not 0. So what would change?
Well, if you say, okay, I have a symmetric one, but I don't have this property,
Yeah.
the thing you have to require is that this map is injective. That's the only thing. And the metric is in general relativity, the metric is invertible, so this map is injective. So this T is G, right, and you get a G minus 1. And you need that. Usually we don't say, but we need that. Right? We usually in relativity we say G, we have a GAB that takes vectors, right? A vector LA, say, and a vector BB, give you a number. So this will be the same as this. And then we have a GAB LB as a vector BA, or whatever. We raise and lower them, and we usually, when we do that, we call this LA again. because it's unique. But for that, all you need is that this map be injective. Not necessarily it has to be symmetrical either. In mechanics, the structure is a symplectic form, which is a anti-symmetric object, which is injective also. That give you from vectors from velocities to momentum.
So I can guarantee that this tensor G or T, for example, is invertible if its determinant is not zero.
Right,
Okay.
right. That's what you need. Let me show you another example which is related to the determinant. Suppose you take a tensor of type 0n. So we'll take n vectors. Okay, and it's antisymmetric. So if I change two vectors on positions, I get a minus sign. Okay? And this vector space, this tensor, I mean the vector space form of all the tensors of this type has dimension 1. Why is that? Because suppose I have a basis and I have one of the components. Then I can switch all the indices around until I order them, and I get the component 1, 2, 3, 4, 4, n. Right? So all components I either this one or minus this one, depending on how many changes you do. Okay? So one number determines the epsilon. So it's one dimension. Right? So every epsilon is equal to some alpha times some other epsilon. Right? Why is this useful? For instance, if you take now, you remember we introduced the A with these two things. Huh? The tensor that takes a vector and covector, and we say that this is a map from B to E. We mentioned just a moment ago. Then I can do the following. I can take a basis, U, and look at all these covectors. All these vectors, sorry. I call them AI. I put them here in the epsilon order like this. And this is just that. And since this is one-dimensional, this vector here, this tensor here, or this number actually, is antisymmetric in all these ones, right? Because if I move one of these, I change, it's a change on these ones. And this is antisymmetric. So this in here has to be also an epsilon. So this side has to be of this form. Because the only input here are the E1, U1, UN, and this is antisymmetric in all. So this number has to be proportional to this number. Right? And this proportionality constant is the determinant of A. You see, this is one way of getting the determinant without using any calculation, basically. I mean, you have to do the calculation, but a definition that does not depend on a particular calculation. And this here, this number here, doesn't depend on the basis. If you change the base, you get the same number here. So that's one way of getting the determinant without. You can get the other invariants of the maps. For instance, the trace of A. This is another invariant you can get from something similar to this, taking one derivative. In the notes is done. So this is a nice definition of the determinant. So what it means that the determinant is zero? It means that this is zero. That means that one of these is a linear combination of the others. And so you cannot get an invertible matrix. Right, so this is one way of seeing the thing you mentioned. If I want to have an invertible map, I need that the determinant be different from zero. And here that means that one of these rows of the map is equal to, one of these columns of the map is equal to some linear combination of the other.
I have a question.
Yeah.
You define the determinants for a matrix analytic from V to V in this case. But could you apply the same thinking with this totally unsymmetric to build the determinants of a metric, for example, which is not a function for V to V?
It's not well defined. Yeah. Basically, when people talk about the determinant of a metric, they are thinking that there is another metric by which you raise the index, make something with the index up and down, and then take the determinant. So what you are having actually is a quotient of determinants. Because you can think of raising one index with one and get something like that, and the other way around. And so in that case some quotients are okay. But there is no geometrical meaning. Isolate, if you say this is a metric, consider the determinant. Probably you can say,
One thing for the Minicals on partial differential equations.
yeah. Just arriving.
No, we came on. We are off and
The lectures are going to be recorded, so you can look at it. So one thing is sometimes the determinant you use in the context of some gauge, things like that. And there usually there is some other metric which you don't see, but you are using to fix the gauge or things like that. For instance, some flat metric in the background or something. And then when you use really the determinant, not to say if the determinant is zero or not is different from computing the determinant. In fact, right? Because if you change basis, you will change the value of the determinant, but not if it is zero or not. So there are things that, like this, if it is different from zero, zero is different as computing the determinant as a number. So, so now we have B, B stars, and then we went to map from B cross B to cross B, cross B star, etc. to the reals. And this way we got all the tensors. Huh? So we have now, from B we have built a whole set of vector spaces. Another way of building vector spaces that we need is a complexification. Namely, instead of having real numbers in the product, to have complex numbers. So one way of getting the BC is say, okay, look at the span of some basis with respect to C. So now you allow linear combinations with complex numbers. Huh? And then you get a space of the same dimension, but with all the components, say, in a basis are complex numbers. So this is basically easy. You can do with complex numbers, you can do with quaternionics numbers, etc. Why do we need the complexification? Because we are going to be looking at subspaces of a vector space, and the subspaces, the easy way of seeing subspaces is in the complex. Once you complexify, that's because if you look at the eigenvalue problem for an operator from B to B, the eigenvalue problem gives you things which are in general complex. And then you need to treat complex things. So in the complexification of the space, you see the real dynamics of what is multiplication for something. So we have to go to complex space. But there is nothing new, you know this. You take some space. You can do other things. For instance, you can take a base and multiply by natural numbers or integers. And here you get something with the flavor of a vector space, but actually it's not, but it's a net or something like that. I don't know the name of this. And this you use, for instance, if you want to have a grid, right, point of a grid. All these points, you say, okay, these are for this vector space. And you can still add them up, multiply by integers, etc., and going from one point to another. So this is a restriction. You can do things like that too. This is not a vector space because here you don't have, given M, you don't have the inverse. You are losing something from the vector space, some properties. But sometimes these things appear. And in our case, how these things appear is because when we do grids, say, we use something like that. And we look at when we do Fourier transform, all the Fourier modes are in these spaces. So it's important to have a good representation of them. They arise like this. And the final way of building vector spaces out of B is the following. Suppose you have a subspace, W. A subspace which is a vector space. So it's a sub-vector space. That is, elements from here, I can say if I have W1 plus W2, this thing times alpha, say, this thing is also in W. So it's a vector space which is contained in the bigger one. It's not, this W is not any subspace, it's a vector space in itself. then we can build what is called the quotient space. And what is this? We will say that W1 is equivalent to W2 and no, let me say, let me change the notation so that U1 and a vector here and is equivalent to U2 if the difference stays in W. Okay? This is an equivalent relations. What it means, do you know equivalence relations? So equivalent relation is a relation which is reflexive. So if x is equivalent to itself, if y is equivalent to x, then x is equivalent to y, and then it has x equivalent to y, and y equivalent to z, then x is equivalent to z. Huh? This is an equivalent relations because if I change U1, if I put U1 in both sides, I get 0, and 0 is in W because W is a vector space, and so it contains a 0. If I do the difference the other way around, so U2 minus U1 is also in W, because if this belongs to W, the minus, that vector also belongs to W. And this is what it says, that U1 is equivalent to U2, and U1 is equivalent to U3, and then I want that U2 is equivalent to U3, so I write U2 minus U3, and I write it as U1 minus U1 plus U2, and here I add a U1 and subtract a U3, so I added and subtracted U1, and this one belongs to W, and this one belongs to W, so this belongs to W because two elements of W stay in W, the sum stays W, right? So this is an equivalence relation. And in equivalence relations there is only one theorem. There is a concept which is an equivalent class. O sea, an equivalent class is a set of all elements U1, say, and they all say, you can get your B, say in this case, and divide B in equivalent classes. So you take an element and look at all the elements which are equivalent to this one. If this is not the whole B, you take another element which is not here and take all the elements which are equivalent to this one, and so on. And these are the equivalence class. So this, now you look at this as a single entity, right, as the equivalent class, some equivalent class. It doesn't depend on U1. U1 is one element, but there could be many. And the theorem says, okay, if I have an equivalent class and I have a set, then the set is the union of all the equivalent classes. And the equivalent classes are disjoint. So U union J is only the element, the zero element. So equivalence relation is, say, like belonging to a football team. The ones that belongs to Palmeira don't belong to Botafogo, whatever, right? And so, but the whole country belongs to one of them. So you can divide all the population by the football clubs they belong to, they fan for. And so here, this is the theorem, says, okay, this here means the collection of equivalent classes, right? And this set is a vector space, that's a claim. V over W is a vector space. In itself. This, I think, you have it as a homework, but I'll tell you how it goes. If I say that this is a vector space, I have to tell you how you sum elements of here and how you multiply them by a number. Right? So remember, this is equivalent class. So I have an equivalent class psi 1, and I want to know what is psi 1 plus psi 2, where these are two equivalent classes. So what I do is take one element from here, B1, one element from here, B2, I do the addition, and look at the equivalent class where the addition is. Okay? And so this is equal to psi 3. Right? Well, you have to, okay, what happens if I take another vector here and another vector here, and I do this? Do I obtain the same equivalent class? That's a question, because otherwise it's not well defined. So let's take another one. B twiddle 1 and that gives me something. And I want to show that what it gives here is the same equivalent class than this, right? So I take the difference, B1 minus B1 twiddle plus B2 minus B2 twiddle. And look at this. This belongs to W. And this belongs to W. Therefore, the sum belongs to W. Right? And so this vector and this vector belongs to the same class, equivalent class, because the sum or the difference belongs to W. So this is, and with the multiplication is the same. So this is a vector space. And I'll give you an example. Suppose you have in 2 dimensions, you have a R2, the plane, and I take some vector B and look at WB, that is all the vectors along B, which are just a multiplication by B. This is this space, this vector space. And now I'll do B with this one. No? You can see all the equivalence classes are these lines, because this vector and this vector, the difference is a vector like this. So all vectors here along this line, their difference is along this line. So the elements of this are lines. All these lines. And the sum of two lines is you say I have say another line here parallel to this one. The sum of this, I have to take one element from here and sum with one element from here, and that give me another element, something like that around here. And this is equivalent class. This is a sum. This construction appears all over the place. So it's very important that you understand this. We, for instance, in physics, we have the vector potential for magnetism. We say this is equal to A plus the gradient of phi. This is an equivalent, this is a quotient like this, but infinite dimension. Or when we say in Newton's theory of gravity, when we have phi, if we add a constant, it's the same thing. It's also like this. We don't, phi is not important, it's only important the equivalent class of all phi's, which are different by a constant, or here by a gradient. These are equivalent classes, they are these objects, and they are vector spaces. When we go to tensor, say we look at this as a tensor, a vector in 3 dimensions, then it's no longer at this equivalent class is no longer a tensor in the way we think of a vector in geometry, because it has this freedom. It's not the same, but it's a vector space. Nevertheless, I can sum things, etc., but they don't have this property of changing on the coordinate transformation and keeping everything. It's another entity, these equivalent classes. But they appear all the time, so it's better that you know them from the beginning. And we are going to see them in many cases. For instance, usually people say that the space of quantum mechanics is the Hilbert space of functions, L2 functions. But the Hilbert space of L2 functions, they are not functions. They are equivalent classes. Why? Because if I change the function at some point, still, when I do integral, the solution is, the result is the same, but the function is different. And in quantum mechanics, all these functions are equivalent. All the functions that depends on an arbitrary number of points are the same thing. And they are not smooth, because you can have some function nice and have some point somewhere else. So there is a quotient there going on. Okay, let's finish. For those interested, we are going to meet at 3 o'clock, so in 2 hours, to help with the installation of Julia and give some hints and see what's going on. Okay? So if you haven't done it, please write your phone number so that we can make a WhatsApp list. And Laura is collecting them, and she will generate the WhatsApp list. Okay? See you.
Actually, I sent the invite link through the chat.
Okay.
So you can just follow the link and you'll be in the group.
Okay. Good. Thank you, Anna.
Welcome.